of Laplace transform and how we use it in circuit analysis. So this lecture will be broken into two parts. Part one will be mostly mathematical part, where we explain the mathematical principles of Laplace transform, its common property, how we can evaluate the inverse transform. So these are the first few points that we will discuss. And then in the second half of, so this is the first half, in the second half of the class, we're going to look into how we implement this mathematical concept of Laplace transform into circuit analysis, and how do we evaluate transfer function, and how can we differentiate between forced and natural responses of a first order network. As usual, if you have any questions and you're joining online or in class, feel free to ask as we progress. So let's start with Laplace transform definition. So by definition, Laplace transform is dictated by this formula over here. F of s is equal to f of t, the integral from 0 to infinity of f of t e power negative st dt. So basically it states that if you have a function f of t, any function, this could be in circuit analysis, could be a voltage, could be current, it could be an impedance. If you have any function f of t and you plug it here in this formula and perform the integration, then you've effectively evaluated the Laplace transform, which is f of s. What does s stand for? S is the Laplace variable and it's the complex frequency j omega. So basically, for the same function, you'll have two representations. You'll have f of t, function.
Miss, excuse me.
Yes,
Before we start, can you give us the brief about the final exam?
I can give you after we finish because we gave that in our first lecture and it's available in Moodle. Okay? So we'll just finish
Okay.
this and I'll give you that. So we
Okay,
said
sure.
that the function can exist as a function of time, f of t, or as a function of frequency, f of s. It's the same thing. So if you remember, we discussed sinusoidal functions and we said that they look like this. And we said that x-axis represents time. And we said that mathematically we could write it as a sine omega t plus pi or plus theta plus a phase shift. And we mentioned that this is one full cycle. We call the duration of a full cycle a period. And we said that this omega, which is the angular frequency, is equal to 2 pi over t. So frequency and time are referring to the same thing. How fast is our function propagating through space, right? And we can plot it in frequency domain. So this plot is in time domain where x-axis represents time, the y-axis represents your signal. You can plot it where x-axis represents frequency and the y-axis represents the power of your signal. And in this case, if this is t naught, this is omega naught, then your sinusoidal signal is a signal with a single frequency at omega naught, right? So this is to say that the same signal can be represented either in time representation or in time domain as an f of t, or as a function of its frequency as f of s. We call this the Laplace pair. So the same function has a pair, either in time or in frequency. And vice versa, if you know the value of f of s, then you can perform what we call the inverse transform, Laplace inverse, to come back to f of t. We call that the inverse transform. Now, in today's class, we're going to do zero integrations because we have the Laplace transform pairs table. So this table gives you all the common function and their equivalent transforms. So if f of t is equal to delta, or a unit step, or an exponential, sinusoidal, all types of common standard functions, and we have their transform pairs. So you don't have to memorize this table. It will be available for you on your final exam. Just learn how to use it properly. So for every function f of t, there is an f of s. Now, for Laplace transform, there are some properties. And when I say properties, keep in mind that the purpose of learning about all these properties is to minimize our calculations to as little as possible. So we can evaluate the transforms without further calculation. For example, we have the time scaling property. What does time scaling means? Time scaling a signal means either shrinking it or expanding it in time. For example, this could be your f of t, and it could start as 0 and end at 1. We can time scale this signal by either A, expanding it, so it can start at 0 but ends at 2, or by shrinking it, so it will start at 0 but it'll end at 0.5. So in that case, this is f of t. Here we have f of t over 2. Here we have f of 2t. So we accelerate time means we shrink the signal, or we expand time means we expand the signal, right? So this is called time scaling. And basically you have f of t, but here and here we have f of at. Time is multiplied by a factor, either for expanding or for shrinking. So the rule states, or the the Laplace transform property states that if you know the original pair, if I have a signal f of t, and I know that the Laplace transform for this signal is f of s, then the Laplace transform of f of at, a time-scaled version of that signal, will be 1 over a f of s over a. What does that mean? It means you'll take this f of s, replace every s by s divided by a, and then divide the entire thing by sa. For example, let's take this signal as our original pair. Let's say I have e power minus 2t, which has the Laplace transform of 1 over s plus 2 from the table, okay? Now, what if I want to find the transform of e power minus 2t over 3? What would be the Laplace transform without any calculations? All you have to do is first evaluate what is the factor. What is the time multiplied by? 1 over 3, right? So this a here is equivalent to this 1 over 3. So 1 over a means 1 over 1 over 3 times f of s over a means we'll take this f of s, replace every s by s divided by a, which means multiplied by 1 over s divided by 1 over 3 plus 2, which is equal to what? 3, 1 over 3s plus 2, right? So this is how we apply the time scaling property. Similarly, we have time shifting and frequency shifting properties, which are all start from the same basic concept that if you know a function f of t has a Laplace transform f of s, and you already know the original pair, then if f of t is shifted in time, and shifted in time means if my original signal, let's say, was, let me edit this, if your original signal was, let's say, a unit step, at t equals 0 it starts increase, then you can have, this would be your f of t, then you can have shifted version of it. If this is 0, then you can have f of t plus 1, which starts here at -1, or you can have f of t minus 1, which will start at 1 instead of 0. So this is called time shifting. Now, the Laplace transform of a shifted version of the original function is equal to the Laplace transform of the original function f of s multiplied by an exponential, which is what we have over here. So if you have f of t minus 2, for example, then, and this has the Laplace transform of e power minus minus 2 t, instead of t it will be minus 2 s f of s. Make sense? So if you shift in time, you'll just multiply by a power equal to that shift value. Clear? Similarly, we have what we call frequency shifting, which is the opposite process. Instead of shifting in time, what if we multiply the function by a factor EAT times f of t? Then in that case, the Laplace transform will be, instead of f of s plus a, which means replace every s by s plus a. So are we clear on properties so far? Let us have a quick example. Let's say that I need to find the transform of e power minus alpha t cosine omega t. Now I already know from the table that if f of t is equal to cosine omega t, then the Laplace transform f of s would be equal to s divided by s squared plus omega squared. This is from the table. The transform of cosine is s over s squared plus omega squared, which is what we have over here. The Laplace transform of a cosine, okay? So now we have the transform of a cosine. Can I find the transform of e power alpha t multiplied by the cosine? So if you look at the properties, which property fits the best? So we have the cosine, but it's multiplied by an exponential function, right? Which means it fits this property, right? We have f of t, but it's multiplied by an exponential. Are we following? Which means we'll take f of s and just replace every s by s plus a, where a is the power of that exponential. So this is what we will do here. We'll say that the transform of e power minus alpha t cosine omega t will be equal to this same f of s, but we said f of s plus alpha, right? So it will be s plus alpha divided by s plus alpha squared plus omega squared. So what did I do here? All I did was simply replace this s and this s by s plus alpha. Make sense? So this is how we apply that property. Now there are many other properties than the three that I just focused on. We can look at them, and the whole purpose of these properties is to help you minimize the calculation. Otherwise, if you wanted to solve for this, you would have had to go and take this value and plug it in this formula in place of f of t. And then you'd have to perform some sort of integration by parts. And it will be a lengthy process, right? So this helps you with minimizing the amount of calculations that you have to do. Up till this point, are we clear? Online, do we have a question? Okay. So
No,
now,
miss.
thank you. So now let's move on to another theory, which we call the differentiation theorem. So we've already established that there are some properties and they are built on your knowledge of a basic pair, f of t, that has a transform of f of s. So if you have a function f of t and you apply the Laplace transform to it, you'll end up with f of s. What if I want to find the transform of the derivative of f of t? What would that be? The transform of the derivative of the function. In that case, we use the differentiation theorem, which is again a simplified formula. The first derivative is s f of s. So we'll just take this exact f of s and multiply it by s. So it becomes s f of s minus the initial condition. Now I'd like you to pay attention. If you notice, whenever I'm referring to the function in time domain, I'm using small letters, right? For f of t. And when I'm referring to the function in frequency domain, in Laplace domain, I'm using capital letters, right? So what we have here is f of s minus f of 0. Now, if you look at this f of 0, is it capital or small? It's a small letter, right? So here we have f capital of s times s minus f small of 0, which means the initial value of f of t when time was equal to 0. Clear? So this f of 0 is time at 0, df over dt of 0 means the derivative of time substituting for every t value by 0. For example, let's say my function is an exponential e power minus at. From the tables, I know that this is the transform of the exponential, the decaying exponential. So the question is, if you started with this pair, e power minus at, which has the Laplace transform of 1 over s plus a, can we find the Laplace transform of d over dt of e power minus at, which is the derivative of my function? This is the formula, right? So it is equal to s f of s minus f of 0, right? This over here is f of s. I'm already given that this is f of s, the Laplace transform. So s times 1 over s plus a, correct? Minus f of 0. So f of 0 means I'm going to go to this function and substitute for t equals 0. So minus e power minus a 0, which is equal to what? Which is equal to s over s plus a minus 1. Make sense? So we didn't have to do the integration. We didn't have to go and find the derivative and then integrate and apply the formula or anything. We just had to use the properties and the theories that we know in advance. Now keep in mind that sometimes when you're applying Laplace transform specifically to electrical circuits, sometimes you're told to ignore the initial condition. So if you're asked to ignore the initial condition, that means you will treat this as it doesn't exist, as if its value is 0. Make sense? Clear? Any questions so far? Okay, so now let's move on to the initial and final value theorems. The initial value theorem states that the initial value in time is equivalent to the final value in frequency, or in other words, the limit of f of t as t goes to 0. So if time is extremely small to the point that we can assume that time is equal to 0, this initial value in time is equal to the limit of s multiplied by f of s, but when s tends to infinity, which means that at extremely higher frequency is almost equal to infinity, and vice versa. So the limit of the final value in time when t is almost infinity, it's extremely large duration of time, is equal to the initial value of frequency. So we call this the initial and final value theorem, and the reason why we will use this in our circuit analysis is because you always have to worry about initial conditions and steady state values, and steady state is basically the final value. So this is where we will apply it as we practice. Then we have the concept of poles and zeros. So last week we discussed that every circuit or system that we design is basically a box, and inside this box we have combination of series or parallel combinations of resistors, capacitors, or inductors, and then we have an input that we feed to this circuit and an output that we take out of the circuit. Now the input and output could be voltages, they could be currents, they could be a combination, it doesn't matter. But we feed it an input and it gives us an output, and basically it goes through a gain. So in other words, this gain or this transfer function, as we referred to it last week, is basically the output divided by the input. And this is the transfer function of a system. So inherently by nature, the transfer function of a system is a fraction, a polynomial fractional value. So as designers, you need to know what are the frequencies at which you're operating your system that you need to avoid. And we call these the poles and zeros. So zeros are values that will lead the numerator of this transfer function fraction to be equal to 0. So any value of s that will lead this numerator to be 0 will mean that the total overall gain will be equal to what? If the numerator is 0, so 0 divided by any number is 0, which means zeros are values of s that will lead the function to be equal to 0. And similarly, we have what we call the poles. And poles are values of s that will make the denominator equal to 0. And if the denominator is equal to 0, that means that our f of s is infinite, or in other words, an unstable value. So we need to identify poles and zeros because when you're designing a circuit, you need to identify which frequencies to avoid, either because they will give you an unstable system or because they will give you zero output. Up till this point, are we clear? Online, are we good? So we'll move to the last
يعني
bit.
not clear too much, but little bit.
Okay,
But
which part?
Miss, I have inquired about the formula sheet.
It
Can
will
we
be
get it in
available
the
in the
module?
final. Yes, you'll have it in the final exam. I will upload it to your model. It will
Okay.
have all this Laplace table and formula, okay? I will upload it
Okay.
for your model.
Inshallah. Thank you.
Okay, so finally, now up till this point, I was discussing the transform, its properties, the poles and zeros, and so on. What if I want to find the inverse transform? What if I have f of s and I want to find f of t? So in that case, I will do an inverse transform. So the inverse transform, if you notice, at the very first slide of this lecture, I gave you a formula, a mathematical formula for forward transform, but there are no formula for inverse transform. So therefore, for the inverse transform, we are stuck with the tables. So these becomes a lookup table. If you have f of s, you'll just go and look it up and see what is the f of t corresponding to it. Therefore, if you want to evaluate the inverse transform, your function that you need to find the inverse of must be in a form that is pre-existing in the common functions table. For example, let's say that I want to find the inverse transform of this function, f of s. So let's write it first. 12 s plus 1 times s plus 3 divided by s times s plus 2 times s plus 4 times s plus 5. Now if you look at this, in the common function table, there's no such thing as this multi-term polynomial. However, if you look at the table, and let me just run real quick to the tables, we do have 1 over s, and we do have 1 over s plus a constant. So what I will do is I'll try to rearrange this or mathematically manipulate it into something that I can find on the table. And for that, I will use partial fractions, a term that you should be familiar with. And I'm going to say that this large fraction was originally 4 smaller fractions, a over s, b over s plus 2, c over s plus 4, and d over s plus 5. So this is what we start with. And then once I can establish or find the values of a, b, c, and d, then I can go back to the Laplace transform. I know that for 1 over s, the inverse transform is u of t. And for 1 over s plus a constant a, the inverse transform is e power minus a t. So, given that a, b, c, and d are constants that we can find them, then the inverse transform of f of s, which is f of t, would be equal to a, whichever the value of a is, times u of t, plus b times e power minus 2t, applying this rule, plus c e power minus 4t plus d e power minus 5t. So now we have a general formula for the transform, the inverse transform, and all I have to do to have a full answer is to solve for A, B, C, and D to find their values. So up to this point, are we clear?
Yes,
Now,
miss.
if I want to find the values of A, B, C, and D, so this will be some pure math here, all you have to do is either use elimination method or comparison method. Let's try with elimination. Basically, to find A, for example, what I will do is I will multiply both sides of the equation by the denominator of A, which is S. So the denominator of A is S, so I'll multiply everything in this equation by S, just to maintain the integrity. What happens is this S and this S will counter each other out. And this S and this S will cancel each other out. And then the next step is that the equations should be true for any given value of S. So I'm going to select the one value of S that will help me get rid of 3 of the 4 unknowns. So if S is 0, let S equals 0. What will happen is that this term will be 0, this term will be 0, and this term will also be 0. And on the right hand side of the equation, the only thing I have left is A. And on the left hand side of the equation, I'm going to substitute in place of every S the value of 0. So it becomes 12 times 1 times 3 divided by 2 times 4 times 5, which means that A is equal to 36 over 40. Up till this point, are we clear? So we've already established that the value of A over here is actually equal to 36 over 40. Similarly, in a very similar fashion or manner, I can evaluate B, C, and D. So I'm going to do B, and I'll leave C and D for you to practice with. So all you have to do, remember, to find the variable value, you have to multiply both sides of the equation by that variable. So in this case, I'm going to, in order to find B, I'm going to multiply everything by S plus 2. Everything is to be multiplied by S plus 2. And these two counter each other out. And these two counter each other out. And then I'm going to find which value will make S plus 2 0, so that everything multiplied by S plus 2 will be eliminated. And that is if S is equal to minus 2. So if S is minus 2, it means A multiplied by 0, C multiplied by 0, D multiplied by 0. And then on the right hand side of the equation, the only variable I have left is B. And on the left side, I'm going to replace every S by minus 2. So 12 minus 2 plus 1 minus 2 plus 3 divided by minus 2 times minus 2 plus 4 times minus 2 plus 5, which is equal to 12 times minus 1 times 1 divided by minus 2 times 2 times 3, which is equal to negative 12 over negative 12, which is 1. So B over here is actually equal to 1. And so on, we can calculate the values of C and D, or of these variables, which will end up with this value over here. So this is how we can perform or evaluate the inverse transform using partial fractions. So up to this point, are we clear? Do you have any question with partial fractions?
No, miss.
Okay, so now this is the first half of our lecture. This is the mathematical principles of Laplace transform. How do I use this, or how does this whole Laplace transform concept apply to circuit analysis? So the whole concept of Laplace transform and how it applies to circuit analysis is that sometimes the problem is too complicated to be solved in time domain. And in that case, it's easier to solve in the frequency domain. So therefore, when we want to use Laplace transform in circuit analysis, it's a three-step process. Step 1, convert or transform your problem from time domain to frequency domain. Then we solve the problem in frequency domain, and then finally we convert back to our time domain. For example, we have this circuit. It's a very simple RL circuit, And the question is find the current ignoring initial conditions and assuming the value of Vt is u of t. So here I have two very important information. I'm told to ignore initial conditions, and I'm told that the value of V of t is u of t. It's a unit step. So what I will do is I'm going to use Kirchhoff's voltage law. What does it state? It states that the algebraic sum of voltages within a closed loop is equal to zero. Or in other words, V is equal, this is V of t, is equal to V1 of t plus V2 of t. Now, we've already established that V of t is U of t. Let's leave it for a moment there. V1 of t is the voltage across the inductor. And we know that from last week that the voltage across the inductor is equal to L di over dt. Plus V2 is the voltage across the capacitor. And from Ohm's law, we know that V is equal to I times R. So if I want to isolate I, let's first divide the entire equation by L and then rearrange it. So it becomes di over dt plus I times R over L is equal to Vt over L. We've already established that Vt is a unit step function, u of t. So 1 over L, u of t. So this is step 1. This is our problem in time domain. And we need to solve for I. The unknown is I of t. Remember, we need to find what is the value of I of t. So now I have a function, a formula with I on it, but it's a differential equation, which is not the easiest to solve. So I'll do the first step, which is convert every term from time domain to frequency domain. So I'll take this term and convert it. di over dt. So the derivative, we've already had a theory for the derivative, which is called the differentiation theorem, when we said that Laplace transform of a derivative is s f of s minus f of 0. So I'm going to apply it here. I'm going to say that this is s I of s, because the name of the function is I, minus I of 0. So this is the first term. The second term, we have a constant, which is R over L, and then I of t becomes I of s equals to 1 over L, and the inverse transform of u of t from the table, we go back to the table here, the inverse transform of, or the forward transform of u of t is 1 over s. So I'm going to write it here. 1 over L times S. So now this is step 1. I've converted from time domain to frequency domain. Next, I am told to ignore initial conditions, which means that this is equal to 0. So my problem in frequency domain is basically S I of S plus R over L I of S is equal to 1 over L times S. And now I can take I of S as a common factor in the left-hand side of the equation, and I'll be left with S plus R over L is equal to 1 over L times S. And therefore, I of S is equal to 1 over S L divided by S plus R over L. Or we can rearrange it by taking this S down, so it becomes 1 over L times S over RL. So this is the problem solved. You already solved for current in frequency domain. But the question was in time domain, which means now I have to go back and perform the inverse transform by using partial fractions. So I'll say that 1 over L divided by S times S plus R over L is equal to A over S plus B over S plus R over L. And then I can find the inverse transform of I of S is equal to I of t. And the inverse transform of A over S is A over U of A of U of t, and the inverse transform of B over S plus RL is B e power minus R over L times t. And all we have to do is just use partial fractions to solve for A and B, which you'll find that A is equal to minus B equal to 1 over R. which is what we have here. And this will be your final value. Up to this point, are we clear? Does it make sense, or we have a question so far?
Can you miss repeat again? What
Which part? Let
the
me
first part?
here. So
Yeah.
up the entire thing
P equal to P1 T.
from here.
This is formula sheet. Yeah.
This is Kirchhoff voltage law. قانون كيرشوف اللي هو الالجبريك sum of voltages. مجموع الفولتيات في دائرة مغلقة بيساوي صفر.
Yeah.
Okay? So this is not a formula. This is a circuit theory. Okay?
Circuit.
That V is equal to V1 plus V2. Next thing I did was evaluate what each of them. V, we are told, is equal to what? U of t from the question, صح?
Yeah.
V1 اللي هو voltage across the inductor. This is a rule. VL is equal to, let me write it here. VL
Circuit
is
formula sheet.
equal to L di over dt. And this is in the formula sheet, okay?
Yeah.
And then V2 from Ohm's law is equal to I times R, right?
Yeah.
And I divide it by L. Everything is divided by L, just to simplify. So this L and this L cancel each other out. I ended up with U of t over L is equal to di over dt plus IR over L. Clear?
Yeah.
So this is what we have here. I just switched the two sides of the equation. Then at this point now I have a problem. This problem is in time domain and it's a differential equation, which is not easy to solve, not the easiest. So now I'm going to use Laplace transform by converting every term to its frequency equivalent. So the derivative converted will be equal to this from the differentiation theorem. Clear?
Yeah.
And this is converted to this. I of t becomes I of s. It's a very simple conversion. Any f of t becomes f of s. I of t becomes I of s. V of t becomes VSS of s, and so on. And finally, we have u of t, unit step. From the table, we know that u of t has the transform of 1 over s. So this becomes this. Clear?
Yeah.
Now, at this
Yes.
point, it was easy to isolate I of s and have this solution, or the value of I of s, right?
Yeah.
And then at this point, all we have to do is to use partial fractions to find the inverse transform, because the question is not find I of s, it's find I of t. So if I already know I
Yeah.
of s, I need to find the inverse transform to get I of t, and for that I did partial fractions. Does that make sense?
Yes. Complete. Yes.
Oh,
Correct.
perfect. So now we've reached to, where am I at? This point, that this is my transfer function.
IT1 to
I
apply.
of t is, A is basically 1 over r, and B is minus 1 over r. So we already said A u power of t plus B e power minus r over lt, right? A is equal to 1 over r, B is minus 1 over r. Clear?
Yes. Clear.
You'll notice that here I've also multiplied by u of t, even though it's not on the tables. And the reason for that is now we're dealing with real quantities. We're not just dealing with a numeric value, we're dealing with a real current. And there's no such thing as negative time. So therefore, to ensure that my current exists only in positive time, I've multiplied it by u of t. U of t basically makes everything prior to t equals 0 by 0. Make sense?
0.
So this is the whole thing. Now I'd like to ask you to pay close attention to this formula. If I am to plot it, let us try to make a plot where this is t and this would be I of t. I of t is basically two terms. There is 1 over r u of t, which is a straight line, 1 over r. So this is this term. And then the second term, which is 1 over r e power minus rl, which is a decaying exponential that is gradually decreasing. So this is 1 over r e power minus r over L t. So I is basically the blue line minus the green line, which is looks like this, correct? So at point 0, 1 over r minus 1 over r is 0, and then it starts to gradually increase, correct? So this red line over here represents I of t. Now, if you notice, I of t will gradually increase, and at some point it will become equal to 1 over r, correct? So
Yeah.
initially, it is gradually, if I plot it separately, it is gradually increasing, and then at 5 tau, or 5 r over L, it stabilizes at 1 over r. This here is what you might have heard of as the transient state, and this is the steady state after it reaches its final attendance. Write your ID. Oh, you've joined online? خلاص, okay, you're good. Okay, so we have the steady state. And if you notice, the steady state follows u of t, which was the input voltage. So we call this the forced, this term we call it the forced response. Why is it forced? Because it's dependent on the external input that we apply to the circuit. We force the circuit to it. While this term we call the natural response. Why is it natural? Because it doesn't depend on the input, it depends on the circuit topology. How is the circuit connected? Is it combination of series or parallels? What are the values of component in it? So we call this the natural response. And if I take the exact same circuit, let me make some space here. If I take this exact same circuit, and this time instead of calculating the current, let's say it's the exact same circuit with the exact same unit input, u of t, and instead of calculating I want to calculate V2. You'll notice that V2 from voltage divider rule, which was already established last week, V2 is R over R plus SL times V, which we already established that V of t is equal to U of t means V of S is equal to 1 over S. And if I try to rearrange this so it looks like the tables, you see that V2 of S is equal to R over L divided by, sorry, R over L divided by S, which is this S, times, these are counter each other, S plus R over L. So this is V2. And if I want to find V2 of t, I need to perform the inverse transform of V2 of S, which means I'll use partial fractions. A over S plus B over S plus R over L, which will give us the exact same shape of output, which is AU of t plus B e power minus R over L t U of t, which is what we have over here. Now, if you notice, the forced response is still a unit step or a DC value, and the natural response is exactly the same, e power minus R over L. If I compare it to the natural response of when we were calculating current, e power minus R over L. So this is to tell you that if you have a circuit, regardless of your input and output values, your natural response will always remain the same, and it will always be linked to the topology of your circuit, so the way it's connected, and to the value of the components of that circuit. So up till this point, do we have a question? Any
No,
questions
miss.
so far? Okay.
No, miss.
So
Thank you.
with that, let us summarize what we've covered today. Today we've covered Laplace transform. We've looked at the first half of this session into the mathematical concept, the definition of Laplace transform, the common functions transforms, and the properties of Laplace transform. And then we looked into how we can use partial fractions to find the inverse transform. And then we moved on to how we implement this into circuit analysis by using the three-step process, which is first converting the problem from time domain to frequency domain, solving the problem in frequency domain, and then lastly, converting back your solution from frequency domain to time domain. We've also looked at the response of a function. We looked at the difference between a natural response and a forced response. And we also looked at how the natural response has nothing to do with the external input. However, the final state or the steady state output always is based on the forced response. Now, if you want to practice with this, I'm going to upload to you a tutorial sheet, but you can also look at chapter 13 of Irwin and Nelms. It will give you more problems and more things to look at in terms of Laplace transform. So with that, we end today's session. If you have any question, you can let me know now. Any questions from those who are joining online? Yes? Yes, they will be uploaded in Moodle. Right now, Moodle is a little bit messy because we are looking at last year's edit. Just give me 1 second. Sorry about that. So as I said, we will upload Moodle tomorrow. Me and Ms. Bilqis will sit together to update and edit the Moodle page so it will be more clear to you. Uh, and we will share the recordings there as well in a separate folder. Any other? Both will be shared. By the way, they are the same content. So if you watch mine or Ms. Bilqis, you can choose whichever you feel more comfortable watching. Okay? It's the third class, but we covered only 2 lectures because lecture 1 was broken into 2 weeks. And I remember one of you asked me at the beginning of the class about the final exam. So just to recap, this module has 2 assessments. There is a group project and there is a final exam. Both equally contribute to your final mark, so 50-50. The group project, we will form a group of 5 or 6 students in group, and you will be given the assessment brief after Eid. But before Eid, I will ask you to self-enroll and you receive email with further details on that. But if you have any questions, feel free to drop me an email.
Miss, about the we give us the brief about the assessment. How it is come, you will give us the formula sheet and you will give us the tutorial or how is will be the final exam?
Okay, for the final exam, you'll be given a formula sheet. I can share it with you in Moodle from now, so you'll know what formulas you'll have.
Yeah.
The exam will have 4 to 5 questions, and it will
Okay.
cover all the topics that we study in the module, which means that if you notice, you'll notice from this point onwards, every topic will be covered in 2 or 3 lectures, and we have about 4 topics. So we'll have 4 questions, each addressing one of the topics. The question will be multiple parts. So, for example, question 1 will have parts A, B, and C, and B will be based on your answer on A, and C will be based on your answer in B and A, and so on. So they're linked together. The 2 weeks prior to the final exam are always booked for revision. And then
Yeah.
we have the Academic Support Center, which can give you extra revision classes the week before the exams.
Revision by you or by doctor or
It will be by me and by Ms. Bilqis.
Miss Belkis?
Okay.
Yeah. There is will be as the tutorial or what?
I will share the tutorial is not an
Tuition?
assessment. It will not have marks, but I will upload it for you in Moodle. So the purpose of the tutorial, because the exam is basically problems that you solve. So the tutorial will help you practice. So the
But
tutorial, I will upload in Moodle problems
the
with their
tutorial,
theory.
but the tutorial will be the question the similar in the final exam or the different?
Similar level of difficulty, not same, not same. Please pay attention. The final exam is not going to be from the tutorials. It's not going to be the
Yeah,
exact revision. Keep that in mind. And it's not
yeah.
going to be based on your memorization. Don't memorize anything. The formula sheet is comprehensive. It has every equation that you will need. Just understand how to use it.
Yeah, yeah. It's
Okay?
better. Yeah.
Yes. Any other questions? Any
Nothing. Thank
questions?
you.
Okay, thank you everyone. Thank you for joining me today. Please take care and I'll see you all next week, inshallah. Thank you.
Inshallah. Thank you. Thank you.